So we've got a real puzzle here, right? On the one hand, diffraction shows us that, yeah, of course, light behaves like a wave. And then the photoelectric effect comes along and says, wait, light clearly behaves like a particle. Um, and we don't have a good answer. And then we start talking about matter, which we'll do a little bit here too. So just a short video on the mysteries of the wave-particle duality. So we come back to the idea of the wave-particle duality, right? Do EM waves behave like a particle or a wave? We've seen evidence of both, right? And so our answer has to be that it behaves like both, not that it is both, okay, but that it behaves by both. And that just means, in some sense, that our metaphors are falling apart. We don't have a good, nothing in Newtonian physics acts quite like EM radiation does. And that's Newtonian physics, is that physical world that we're really familiar with. And this is called the wave-particle duality. And that leads to some really strange and interesting things when we start talking about the way light interacts with itself, and that's what we'll turn to now. Stranger surprises, it says. What are those strange surprises? Well, let's see. Let's first talk about mass and waves. In the 19th century, physicists began to join electric and magnetic ideas into a single force. So we know that, right? We talked about electromagnetic force. That convinced other people that maybe there was something going on with matter and waves. If radiation was really like a particle, you know, if an EM wave was really like a photon, maybe matter, which we think of as a particle, has some aspects of a wave, which is ridiculous, right? Why would you think of, you look at this cup I have in my hand here. What makes you think that could behave like a wave? It doesn't really make good sense, intuitive sense to us. But it turns out that it's right. And that's the thing with quantum physics. What you think is going to make sense isn't always what is going to happen. So what is the wavelength of a particle of mass? Well, our wavelength is Planck's constant divided by our momentum, p. Light has a momentum, which is strange to us because it doesn't have mass. We learned that p equals mv, right? There's a little bit more to momentum than mv. Energy, because of the energy of light, it also has a momentum, but it's a small amount of momentum. So for light, that h divided by, remember h is very small here, our momentum is also very small. So the wavelengths can be of reasonable size when we talk about EM waves. But if mass is going to have a much larger momentum, so our wavelengths are going to be really tiny. So let's see if we can think about how small that wavelength is. If we take an average particle of dust, a small bit of matter, in other words, that's 10 to the negative 16th kilogram, right? That's pretty tiny. It's moving relatively slow, okay, 1 meters per second. It's got a momentum of 10 to the negative 16th in base units. Its wavelength is equal to 6 times 10 to the negative 18th. So if you remember, visible light has a frequency on the order of 10 to the negative 6. Really high energy gamma wave has a wavelength on the order of 10 to the negative 18, or 10 to the negative 14 rather. So this is 10,000 smaller than a really high energy gamma ray. So it's very hard to observe. But it turns out that it was correct. How could we figure that out? Well, people started thinking, well, what the smallest bit of matter that we can deal with is electrons. And what they did was they started shooting electrons at a diffraction grating, right? So just like light went through a diffraction grating, and remember we saw with those waves, it diffracts once it goes through this. The light goes through that little slot. It creates a wave that goes out in all different directions. Um, and it turns out the same thing is true with electrons. You put it through a small slot like that, and it creates diffraction patterns like the one shown here. So matter has a wavelength, which is weird, right? It's really strange. And so just like the electric and magnetic world are kind of joined together by an electromagnetic force, here the mass and wave worlds at the quantum level start to join together, and we need to start thinking about those two things as interchangeable.